So now that we have antiderivative concept, let's talk about things that worked with derivatives and think about whether they'll work with antiderivatives. One thing we really liked for derivatives was the constant vertical multiplier rule. So let's give ourselves a little function to play with. If f of t, little f of t is e to the t, what is big F of t, do you think? What's the antiderivative of e to the t? What function, when you take its derivative, is e to the t? Well, e to the t. Or you could write that as the integral of e to the t dt is e to the t plus a constant. So, do you think the vertical multiplier rule will work if I put a vertical multiplier, a multiplier out front, on e to the t? So we could say, what if g of t equals something like 8 e to the t? What do you think big G would be? What function, when you take its derivative, gives you 8 e to the t? Still 8 e to the t? Or you could say the integral of 8 e to the t dt is 8 e to the t plus c. Right? Or another way you could write it, you could write integral of 8 times e to the t dt, and then you could take that integral, take that 8 and move it out in front of the integral. Say 8 times the integral e to the t dt, which would be 8 times, what's the integral of e to the t dt? We said it's e to the t. And then it's a little shady, or a little ambiguous. Do I put the plus c out here, or do I say 8 e to the t plus c like that? And it turns out it doesn't really matter most of the time. If c is some constant I don't know, then 8 times c is also some constant we don't know. So we would usually write it like this, but it's also okay to write it like that. So we can summarize by saying you can move a constant multiplier or divider into or out of an integral. So you could say the integral of 2x over 100 dx, you could write that as 2 integral x over 100 dx. You could write that as 1 over 100 integral of 2x dx. You could write that as 2 over 100 integral of x dx. All of these are equal. You can move multipliers in and out. Got to keep them on the appropriate side of the fraction bar, of course. And what is that integral? Well, maybe it's easiest from here. What's the antiderivative of 2x? Well, what function when I take the derivative gives me 2x? It would be x squared, and then plus c. So that works just the same as if we were doing derivatives, right? I know some people have trouble thinking of moving things onto and off of the fraction bar, but let's give another example. Let's say like 30 over 5x prime. You could call that 30 of 1/5 x prime, or you could call it 1/5 30x prime, or you could call it 30 over 5 x prime. All of those are equal to 30 over 5. So constant vertical multiplier rule saves us a lot of time, just like for derivatives. All right, what else can we say? Can we say the integral of x times 2x dx? What can we do with that? Can I move the x out front? So we'll put question marks there. Can I say that's equal to x times the integral of 2x dx? See if you can check that. It's kind of tricky. Desmos doesn't have an integral, an integral like this where we we're just saying take the antiderivative. Desmos can't take an antiderivative formula for us. So to check stuff, we have to be a little clever about how we get Desmos to do derivatives to check things instead of antiderivatives. What's your impression here? Do you think this works? Well, x is not a constant multiplier, so the constant multiplier rule would not apply, and so we're guessing that this is not allowed. So we'll say, but x isn't a constant multiplier. Well, can we do anything to rescue it? Can we say integral of x times 2x dx? Well, can I break it up? Integral of x times integral of 2x dx? Well, there's a problem right away. Any integral sign should have a dx or dt or whatever attached to it. Let's just kind of pretend that that one gets there. Rather than saying, well, I only have one dx, I shouldn't have two of them in the product, which is kind of true. But let's follow this to its logical conclusion. What's the integral of x? Well, what function, when I take its derivative, gives me x? It should be x squared, but I need a 1/2. So when I take the derivative and the 2 comes down, it gets ambushed by the 1/2, and I'm left with x. And then integral of 2x is just x squared. So altogether we get 1/2 x to the 4th. But go ahead and check that. What do you get? How do you check it? You'd say 1/2 x to the 4th prime would be 1/2 4x cubed. And is 4x cubed equal to x times 2x? Nope. So we can't take a product and break it into the product of two integrals, just like we can't take a product and take the derivative of a product by taking the product of the two derivatives. What's the better way? And by better, I mean actually works. We could say that this equals the integral of 2x squared dx. And what do we do from there? We would, well, I would move the 2 out front to integral of x squared dx. And then what's the antiderivative of x squared? What function, when you take its derivative, gets you x squared? Well, you'll need to start with an x cubed. And then when you take the derivative, the cube comes down in front, and we don't want it to be there. We need something to get rid of it. So I'm going to say 1/3 x squared. And let's check that by taking the derivative. So all of that prime, we get 2 times 1/3 times 3x squared. And that simplifies to 2x squared. So we're good. So the good news about integrals is you can always check your integral answer by taking the derivative and making sure you get the original function. So not only can you check it, you should always check it, because it's really easy to make mistakes, but it's really easy to check. So you should basically be checking every integral formula you do by taking the derivative to make sure you get back to the original thing you were taking the integral of.